Let's talk about polar coordinates. In class, we did a little example where we had we're surveying a farm, and the farmhouse is right here at the origin. And one surveyor says to get to a rock out here, we go 5 kilometers out from the farmhouse, and we make sure we point ourselves first in a direction that's 30 degrees north of east. And the surveyor would probably use degrees, but we're trying to use more radians more often. And when we talk about this subject with polar coordinates, which is what we're leading into, we often use radians, but there's nothing wrong with degrees. So the question is, the other surveyor we were talking about likes to use what's called easting and northing, or in other words, just the x and y coordinates. How far east do I have to go, and then how far north to get to this same position, that same rock? Okay, that's exactly just what are the x and y coordinates of this point. And so if you tell me this alternate description in terms of length or distance from the origin and direction to go from the origin, can I get x and y? And indeed I can. We just write down the equations for this right triangle. We just say y divided by 5. That's the ratio between something we want and something we have in a right triangle. And we just figure out which ratio that is. Oh, that's sine of pi over 6. Now that happens to be a simple number. We've memorized that. You guys are doing pretty well on that. That's 1/2. And so that tells us that y is just going to be 5/2. Okay. But let me actually go back a sec. Let's not evaluate the sine pi over 6 for a second. I intentionally made it easy, but let's pretend we didn't know it. Y is 5 sine pi over 6. That looks like it's a general formula. If I change the 5 to a 7, probably the 5 would change to a 7 here. If I change the pi over 6 to some other angle, probably the pi over 6 would change here as well. Okay? And there's another perspective on this as well, which is that what if this weren't a 5? If this is a 1, let's draw a little unit circle in here. If I were instead getting this point, and the x and y coordinates of this point on the unit circle, then we know what the coordinates of that guy are. Our sort of modern definition, our more recent definition from this class of cosine and sine are just that those are the coordinates of that point. Now, what did we really want? We wanted a scaled up version of that triangle. But by similar triangles, that just inflates this distance by 5. It multiplies this distance by 5, so this guy becomes this guy, and inflates this guy to become this guy. And so that's why we're going to get, for the y coordinate, 5, the radius of the new circle. We're really inflating to a bigger circle here. 5 sine theta. Let's see if you can see that. Yeah. Okay. Oh, not very good handwriting, sorry. Okay. So that's another reason why it's going to be, here's our general formula. It's going to be, let's call this r for radius, and let's call this theta for our usual formula for angle. Okay. And so our general formula is just going to be its radius or distance, or r sine theta. Okay. So what about x? Well, we could do it either way. X over 5, that's a ratio of sides in a right triangle, and that's equal to the cosine adjacent over hypotenuse is cosine pi over 6. Now that happens to be root 3 over 2. And so x is just going to be 5 root 3 over 2. But it's more interesting. Oops. Yep. It's more interesting if we look at the formula without evaluating that. X equals 5 cosine pi over 6. And so we have a very, very similar formula. It looks like x is r cosine theta. And again, that's another way to see that is you're taking x equals cosine theta on the unit circle, and you're saying, oh, wait, sorry, I'm not on a unit circle. I'm 5 times bigger. And so it's just going to be 5 cosine theta. If this 5 were changed to an r, any other value, we're going to get r cosine theta. So this is 1/2 of the conversion between rectangular, also called Cartesian, because it's from Descartes, and polar coordinates. Okay, so we've got x, y, our standard idea of how to take a point in the plane and put numbers on it. And now we've got r and theta, which are called the polar coordinates of a point. And that's a way to describe things where you do what I said the first surveyor was doing. Describe a point in the plane by the angle you have to go out to get to it and the distance you have to go to. The distance you have to go to get to it. And let me just summarize half the conversion here. We've seen that x is r cosine theta and y is r sine theta. Okay. So before we get to the other half of the conversion, let's just think a little bit. This is getting pretty busy. Let me just think about polar coordinates in its own terms. It's not all about converting back and forth between rectangular. Part of the wonderful thing about polar is that it's just so useful in its own terms. So, for example, suppose I have I'm going to draw some concentric circles. 1, 2, 3, 4, just to get an idea of things. And let's suppose I have a point right here. And I want to figure out what are the r theta values for that guy. Roughly. Think about that for a second. What's the r? Remember, r means distance from the origin, and theta means the angle that you'd have to go in from the origin to get there. So what we want to do is we want to connect that to the origin. And so we're looking for this angle theta. And then the r is quite easy since I did these concentric circles. The r is just how far it is. Well, I happen to put it right on the circle 3. So r is going to be 3. And then theta, well, let's see. That looks like it's pi over 4, 2 pi over 4, 3 pi over 4, roughly. I'll make these wiggly lines, I guess, because it's all about approximation. Now, what about if we did a point, say, down here-ish? Okay. So let's see. What's the r theta for that guy? Well, r, it's between 3 and 4, so it's about 3.5 approximately. Okay. And then what about the theta? Well, let's see. Let's crank it around all the way over. Oh, yeah, put the little connecting rod there. Okay. I tried to draw it a little bit past the 45-degree position, so it's some angle that's a bit more than 1, 2, 3, 4, 5 pi over 4, but less than 3 pi over 2. It's looking roughly about 4 pi over 3, because I was using red for that. Okay. Roughly. And who knows, maybe 4 pi over 3 isn't a particularly good approximation. Maybe it's actually something where I want decimals or something like that. But I just want to get a feel for it. Now, here's the tricky thing about polar that's really, we've experienced this before. It's about coterminal angles. We could also describe that as 3.5, comma, we could go around this way. Let's suppose it was right at 4 pi over 3. That's the same. That's coterminal with minus 2 pi over 3. Or we could even we could replace that with 10 pi over 3. All those coterminal angles. So that's a little bit of a weird thing about polar is that there's multiple answers to these guys for the theta. And there's an issue about r that we'll get to later, but I tend to de-emphasize that lately. So the main thing is that the theta is not always completely specified. And so we might have to be careful about that. Okay, so I'm going to do another video about converting the other way.